For every, how many comparisons are required? 8 comparisons of how many bits? 7 bits.
7 नहीं है, ये तो
Seven.
डायरेक्ट मेट था ना,
8 comparison of
10 मेट,
10 bits. And for direct match, single comparison of what?
7 bits,
And for 32A, how many comparisons?
32 comparison,
32
comparison of 12 bits,
comparison of what?
12 bits.
12 bits. So if we increase the associativity, we not only increase the number of comparisons,
बिट्स को भी बढ़ा रहे हैं,
but it also increases. So the comparator size is increased or reduced?
इंक्रीज
Comparator size.
बड़ा होगा,
The comparator size is increased. Which type of comparator is used?
बाद में
If you look at comparator, so there are different type of comparator. Equal comparator, greater than comparator, or less than comparator.
इक्वल टू कंपेयर,
Equal to comparator. How does it equal to comparator? Okay, now how would you have an equal comparator? If you look at this now if you remember from your digital logic design course, if you want to have a 4-bit comparator, okay. So if I want to compare A with B, if I want to compare A with B, so let's see the field of A3, A2, A1, A0, B3, B2, B1 and B0. If both are equal, what does it imply? A and B0 are equal?
इक्वल
When equal will be 1? Equal will be 1
when all the bits are equal,
when A3 is equal to
B3,
B3 and it's an AND condition.
yes sir,
Then
A2 equal to
A2 is equal to
B2,
B2 and A1 equal to
B1,
and A0 equal B0. Now let's just we have a 4-bit comparison. We are only doing a 4-bit comparison. Okay. Now if you look at here 4-bit comparison, so can we do it like this? A3 equal to B3. Okay. Which gate has this property? When both are 0 0, it will give us 1, and 1 1, it will give us 1.
XOR,
Exclusive NOR.
exclusive NOT,
Exclusive NOR. So if you want to have a 4-bit comparator, so can we write it like this? A3 B3, then A2 B2, then A1 B1, then
A naught, B naught,
A naught B naught, and then which gate do we need to follow it?
AND gate,
Okay, now if you look at for in this example, direct line cache, how many bit comparison is required?
4 comparisons,
7 bits comparison.
7 bits,
For A2 associativity cache,
10 bit comparison,
10 bit comparison. So actually if we increase the number of bits for the stored tag field, so the overhead is increased. The overhead is increased. The overhead is increased. If you use more gates, there will be more delay. If you use more gates, there will be more delay. If there will be more delay, there will be more power consumption. Gee, agreed?
yes sir,
So these are the things that we need to consider while designing a cache.
मतलब there is a trade-off between conflict misses and associativity.
Yes, there is a trade-off between, so in the direct map cache there are more conflict misses. But this conflict misses, more conflict misses. What is the advantage? Simplicity. Because you don't need a replacement policy. You just kick that out.
Yes sir,
But in associative cache you need a
replacement policy and as well as you
need
size of
also
the
a
comparator.
replacement policy. And not only because it also depends on the number of comparisons that are required. Okay, now this is just like from the hardware perspective. Now we look into more detail again. We need into more detail. Okay. These are just like simple details. Now we need to more detail. How does it happen actually? How does it happen actually? Now So now let's assume we have some main memory block address. We have some memory block
address
What is the size of that address? बताने जल्दी बताएं.
2 की power
No, in this example,
26.
26 bits. So we have this main memory block address. So the memory block address has byte offset, and then index field,
So take field.
and then tag field. This index field will go into a particular set I.
Yes, sir.
This index field will go that which set I will be accessed. Then how many comparisons will be there? How many comparisons? A comparison. So actually what will happen? So now if you look at here, if you look at this cache line 0, so actually we have for this cache line 0, so we have what? Tag 0. For cache line 1 what?
Take 1.
Tag 1. And up to what?
Take A minus 1.
Tag A minus 1. So what happens? So what you are doing? You are now comparing this tag field.
With the all takes.
You are now comparing this tag field. With what? Tag, not only tag 0, but also V0. Why V0?
Valid है.
Valid. Whether the cache line is valid or not. So now we are only, if it means the tag 0 and valid 0. So if valid is 0, no comparison. Whatever, even if it's same. Okay. So tag is 0, valid is 0. Then it will be compared with what? Tag 1 and
Valid 1.
valid 1. And after how many comparison?
A minus 1.
A minus 1. So how comparison will be? So if this matches, now okay. Now let's assume that there is a match. There is a match at K. So there is a match at tag K and valid K. So what is it? What is it, guys? Said valid K is 1. If valid K is 1, if valid K is 1 and tag K matches with this field, if there is a match, they are same. What does it imply? It's a very good. It's a hit. Now, when it's a hit, when these two conditions are satisfied, the first condition, the corresponding valid bit is 1, and
Take matches.
the stored tag field. This is stored tag field. The stored tag field matches with the
Address take field.
address tag field. The stored. So it will tag K. So can we write like this? If valid is 1, can you write it like this? If valid bit is 1, first condition, valid bit is 1, and stored any of the stored tag field matches with what?
Address take field.
Address tag field. What does it imply?
It is a hit.
It's a hit. When there is a hit, what should we do now? Let's do some read operation. What should we do now?
Read करेंगे cache से.
We should read which field of the cache line.
Data.
No. So if you K, so the data field. So now there is a cache line K. Cache line K. For a cache line K, how many bits are there? बताएं.
एक valid bit था.
Valid bit,
Dirty bit था.
dirty bit,
Take था.
tag and
Data bit.
data field. What is the size of this data field?
64 bytes.
Byte. So if the valid is 1, now its valid is 1. This tag field matches with the tag field of the memory. It's a hit. So this data field is provided to which?
To
the
processor.
And now it's a hit in the cache. So this is what is happening inside the cache. Inside the cache. Now this is the condition when there is a hidden. When there is a miss in the cache, what should we do now?
Memory से उठाएंगे data.
Okay. When there is a miss, what does it imply? All the tag fields does not match.
Mismatches.
there is a miss. When there is a miss, if it's a direct map cache, we just replace the line. Why?
वो कोई policy
When there is a single
One
line. But if there is any associative cache, if there are multiple lines, we need to evict one of the cache line. So what if there is a miss in the cache? So from this cache line, we need to evict
one cache
one
line.
of the cache. Let's say there are 4 seats and there are 40 students, and I request one student to come on the seat, and all these seats are filled. One has to go out.
Yes, sir.
So actually, we need to decide which one will
Go out.
go out. So you need a replacement policy. So the replacement policy for direct map is simple. Why it is simple?
एक cache line है वही
This is a single cache line. So if the tag field does not matches, when there is a miss, the new block is brought in, and it will replace
the old one.
that one. But if there is a multiple line, then we need to decide. Now if it is one seat, only one seat here, and you say okay, it's replacing here. It's very simple. When one guy is sitting and the new is coming, the old will go out. It's very simple. So, which line will be evicted is based on the replacement policy. And there are different replacement policies. First in, first out replacement policy, least recently used policy, least frequently used policy. There are different policies. We will study this policy in more detail later on. Okay, but now for this one, so okay, now when there is a miss in the cache, so now this is there is a
Miss in the cache.
miss in the cache. What should we do now?
We have to
When there is a miss in the cache, we replace one of the cache lines. Let's assume that line is M. That line is M. So actually now we replace it with the cache line M. Cache line M. What will be its valid field? Valid, dirty, tag, and data. So when we bring the new cache line, so we set its valid bit to
one.
1. Now let's assume if we have this main memory block, so let's assume this is main memory block T, and this is some data here. You bring the whole block from here and store it into the data feed. Okay. Valid bit is set to 1. Dirty bit is set to 0 because you are just bringing your, it's not yet modified. How do you set the tag field? How do you set the tag field?
Memory block से
No, memory block. देखिए, ये तो data field है. This is not the data field. How do you set the tag field? No. Tag field is this. You store this tag field here. Now let's assume this tag field is okay. Now if you look at here, if you look at this tag field, let's assume this is 32A cache. This is 32A cache. So can we write it like this? So can we divide this cache line like this? A26. So now A25. Am I right?
Yes, sir.
So what is A05 to A00? Offset field. What is about index field?
A06, A14,
6 plus 8.
14,
14. ठीक है? Then A13. And then A14 to what? How many bits?
12 bits.
12 bits. This 12 bits will be stored here where?
In the take field.
To the tag field. And it depends on the tag field will be different. Now let's assume the tag field is what? How many bits are there? 12 bits. So let's assume I am writing this in hexadecimal. Let's assume that the tag field is 3F2.
2.
3F2. What will be stored here? 3F2 will be stored here where? 3F2 will be stored. What will be stored in the data field?
जो data है उधर
Data. Now it depends on the data. Let's assume this is 6, 3, 9, 1, 2, B, and so. So this data 6, 3, 9, 1, and this. How many bytes are there? 64 bytes. So that this data field from here will be stored here. Okay, agreed? Okay, now this is very simple for when you are reading the data. Things will be complicated when you are writing the data. When you are writing the data, now if you look at here, now let's assume when you perform, okay, now if you look at here, this is man memory block T, and this is the most significant byte 63, am I right? What is this value? 63? What is this?
62.
Byte 62? Now let's assume if we overwrite this byte and we change it from 91 to 35. So now when there is a hit in the cache, when there is a write hit, next time you have a write hit. So actually if this value is from 63 to 35, when it's changed from, so now the data has been changed in the cache but not in
Main
memory. So in this case, what we do?
30 bits should be on.
So it means that now we have two copies of the data. We have
Two copies.
two copies of it. One is in what?
Cache.
Cache. Other is where?
Memory.
Main memory. So if we have written into the cache, let's assume we bring it the block in the cache. Okay? We store it. First in the base, we bring it the block here. Next time when there is a write to the same cache line, so there is a write hit. When there is a write hit, so what happened now? The block is now modified. When the block is then modified, so now there are two options. You store this modification here also and also
In memory at the same time.
But this will be very costly. This is very
Costly.
To avoid this cost, what do?
30 bit को on कर लेते हैं.
We update
30 bit.
30 bit to 1. It means that now this copy and now this copy are not same. When should we update the memory location? When should we update the memory location?
ये जब सर हम इसको निकालेंगे इसकी जगह दूसरी
When
लाइन
this block
आएगी
will be replaced. This is the purpose of the dirty bit. Okay. So now we will study the cache replacement policy. The cache replacement policy. So in a cache replacement policy, the cache replacement policy. This is used when all the cache lines within a set are occupied and there is a new cache line. There is a new cache line. When the new cache line arrives and the set is full, then we need to decide when of the block to evacuate. Now if we have a direct map cache, so the cache replacement policy is very simple. Now let's assume if we have set I, and to this set I multiple blocks can be mapped. Let's assume when a block A is resident in a cache, and when the tag field of A matches with the tag field of the incoming block address, there is a hit, no problem. When the problem will arise? When there is a
miss.
When there is a miss and there so let's assume we have like word 0 of block A, there will be a hit or a miss? Hit. If we say word 5 of block A, hit or a miss? Hit. If we want to access word 9 of block A and suppose that A and B are mapped to the same set, what we need to do? We will evacuate A and replace it with B. So in this case it will be a hit. In this case it will be a hit. Let's say if we want to access word 3 of block B, what will happen?
Miss.
Miss. When there is a miss, what do we need to do? Bring the block from there. And since in our direct map cache, each set contains only one cache line. So the replacement policy is
simple.
When the problem arises.
So there are multiple cases.
When there are multiple lines within the cache. When there are multiple lines within the cache, it means that now we need to decide the victim candidate. What is the victim candidate? So we need cache replacement policy. We decide the victim candidate. So if you look at here, so there, let's assume we have 4 cache line 0, cache line 1, cache line 2, and cache line 3. What is now the associativity? What is associativity now? In this example.
4.
So when a new block arrives, so you need to decide which cache line to replace. Whether CL0 will be replaced or CL1, CL2 or CL3. Now if you look at the cache, so now we have a set I. This replacement policy, the replacement policy is applied at a set level. The replacement policy is applied at the set level. So the replacement policy decides which cache line to replace when the set is full. When the set is full. Okay, when the set will be full? When the set will be full?
All bits available.
So the set will be full when all valid bits are
1.
1. When all valid bits are 1, so it means we need to kick one out of the block. Now if you look at the cache, so now let's take this cache set I. To this set I, multiple blocks will be mapped. Multiple blocks will be mapped. Okay, now let's assume if there are S sets, how many sets are there here? If you look at here, how many sets are there?
S sets.
S sets. Which main memory block will be mapped to set 0?
0.
Block 0 will be mapped here.
S and
1 will be mapped here. I will be mapped here. Why I?
Set I.
Set I. And then S minus 1. What about S?
S will be set 0.
Set S. So which block will be mapped here? 0, S, 2S, 3S, and so forth. So on. And to set I, how many blocks will be mapped? I, SS plus I, 2S plus I, 3S plus I, 4S plus I, and so forth. Now if you look at here, these blocks that are mapped, let's assume there are M blocks. These are M blocks, and this is A associativity. So typically, M is very larger than A. Why M is very larger than A?
Main memory ज़्यादा होगी और cache
The memory size is much larger than A. So this M is very larger than A. Now all the blocks that are mapped to this set I are I, S plus I, 2S plus I. What is S?
number of sets.
Number of sets. So now we are assuming that we want to apply this replacement policy on set I. We want to apply the replacement policy on set I, and all these blocks H, A, B, C, all these blocks belongs to I, S plus I, 2S plus Y, 3S plus I, 4S plus Y. नहीं समझे यही चीज मैं रिपीट करता हूँ.
Okay, sir.
Okay, so maybe this block H, is maybe S plus 5I, maybe this block A is S plus, maybe this block A is I, maybe block B is S plus 2I, so forth. Okay, sir. Now, it means that all these blocks are mapped where?
The same cache line. Same cache set.
All blocks are mapped to the same
cache set.
We are not considering the blocks that are mapped to the different set. We are not considering the blocks that are mapped to a different set. Because the cache replacement policy is applied at the set level or at the cache level?
Set level.
Set level. So we assume that this H, A, B, C, A, D, all these blocks are mapped to a particular
cache set.
Okay. Now if you look at here, there are two type of blocks. This is a block reference point. When the block is reference. When a block is reference. Let's assume this block is reference at time t0. This block is reference at time t1, t2, t3, t4, t5, t6, t7, t8, t9, t10 and t11. Okay. So this block is referenced at this time. Okay. Now initially we assume that the cache is empty. The cache is
Yes, sir.
empty. When the cache is empty, what will happen?
All the sets will be empty.
When the cache is empty, what will happen?
Where
All the value will be 0.
0.
When the value will be 0, you access cache line H. Where H will go?
CL not will be.
At which time it is placed?
Time T not.
T0. It's a hit or a miss.
It was a miss.
What will happen to the valid bit?
It will become 1.
Valid bit will be 1. The valid bit of which cache line?
CL not.
CL0. Next time, there is an access to block A. Where block A will go?
CL1.
H is still there.
That comes time T not. Yes, sir.
Hit or a miss?
Miss.
Okay, maybe in the meanwhile H is also reference again. But I am not considering that case. Okay. Then, what about B?
B भी
Okay, what will
आएगा
happen? Now valid bit of CL0 is 1. Valid bit of CL1 is
1.
1. Next time, what will happen?
B CL2 में आ जाएगा. Yes, sir.
Hit or miss?
Miss.
What about C?
C भी आ जाएगा. Not. Miss.
Now,
A hit होगा.
there is a hit. Hit? Agreed?
Yes, sir.
Do you need to replace?
No, sir.
No. Okay, now when there is a hit, there are two possibilities. It's a read hit.
That's
If
right.
it's a write hit. If it's a read hit, what will happen?
तो रीड कर लेगा डेटा जो उसका है.
Data will be read. When it's a write hit,
Dirty bit भी
the
आना
dirty bit will be set. Okay, again, dirty bit of which cache line will be set?
CL1.
CL1. So if let's do. So if this, so can we, if we write it like this, that if it's a read hit, then there are two things: read or a
Right.
write. Right? If in case of write, what will happen?
Dirty bit 1 होगा.
Dirty bit will be
Set.
set for which cache line?
For the corresponding cache line.
For the corresponding cache line. What is corresponding cache line?
CL1.
CL1. The relevant cache line, dirty bit will be set. No problem. We don't need to do this. Now there is
a problem. D अब आएगा तो.
now there is a block that is D, not present in which block will index?
फर्स्ट इन फर्स्ट आउट है ना तो.
First in, first out.
तो इच को हम रिप्लेस करेंगे.
Okay. So actually now D will come. So now D
T5 पे आएगा.
it is come. D will replace H. Now it depends on. Now if it will replace H. If it replaces, now it depends. Now if let's say you are now replacing H at this point. Replace H. There are two possibilities. When dirty bit is 0, we just replace it. When dirty bit is 1,
मेन मेमोरी में उसको लिखा जाएगा.
update the memory. So when the dirty bit is 1, so update the main memory contents. How do you update the main memory contents?
राइट करेंगे उधर जाके.
It will perform a write operation on the memory. Which field of the cache line will be updated?
डेटा.
The data field. It will read the data field. But now it has been modified. It will go to main memory and that will update that corresponding main memory block at the block address.
Yes.
At the
ब्लॉक
at the block address. At the block address. Then you have AT1, BT2 and CT. Now again A. What will happen?
हिट होगा.
DT5 hit.
Yes sir.
Then again block D.
हिट होगा.